Okay, section 3.7. I'm sorry, section 3. Did I say 3.4? Section 3.7 is the last section in chapter 3. But this is the last section for the chapter. It addresses variations. There's 3 types. There is what we have called a direct variation. And we say y varies directly as x. And the equation in general would be this right here. K is referred to as the constant of variation, whose value would be determined by using experimental data. So this is the constant of variation, or the constant of proportionality. All right. With direct variations, it's called a direct variation because if x's value increases, y's value increases. If x's value decreases, y's value also decreases. That's why it's called a direct variation. We're also going to look at what's called an inverse variation. We say y varies inversely as x, and you would write the equation this way, where your constant of variation is in the numerator and x appears in the denominator. Okay, so if you ever see variables following the word inversely, those variables will be found in the denominator. All right, and then finally we have what's called a joint variation. By the way, inverse variation means that, like, if x's value increases, y's value decreases. If x's value decreases, y's value increases. So this is an inverse variation, a relationship between x and y. You could have a joint variation, whereas we would read it this way in general: y varies jointly as, let's say, 2 variables, w and x, and inversely as z. So unlike direct and inverse variations, joint variations involve more than 2 variables. So to write this variation as an equation, y would be equal to k xw, and inversely proportional to z. So this would be the way to translate these words into the equation, which represents a joint variation between the variables x, w, z, and y. And it's the interplay of these 2 variables that affects y's value. For instance, if x and w are held fixed and z increases, y would decrease. If x and z are held fixed, as w increases, y would increase, and vice versa. If w and z are held constant, if x increases, y would increase. If x decreases, y would decrease. But it's interesting to note how y is affected by the increase or decrease of all 3 of these, as there would be a more complicated interaction between those there. Okay, so on page 388, I would like to work on several problems in our textbook to illustrate these various types of variations. So we're going to go to our textbook, page 388. All right, so variations, section 3.7 is on the docket. And I want to go down to like problems 12 through 20, okay? As always, ladies and gentlemen, please do take some time to look through the examples in the section. That always helps you to better understand what's going on in the sections. All right, so what we're going to do now is we are going to go through some problems here. And I'm going to go through problems like some of these in 12 through 20 says. Number 12, it says for these problems, they want us to write a variation model using k as the constant of variation. Number 12, the simple interest I on a loan or investment varies directly as the amount A of the loan. To translate that into an equation, which would represent this variation, I is the dependent variable, so I would be equal to the constant of variation, K, and the interest varies directly as the amount of the loan. So for problem number 12, those words would translate into this particular variation. That's called a direct variation. Yeah. Any questions? Number 12. All right. Number 14, it says the time of travel T is inversely proportional to the rate of travel R. So number 14 here, the time T is inversely proportional to the rate or the speed with which we travel. And therefore, this is an inverse variation. You do see the word inversely in here. And as a result, the equation would have the rate appearing in the denominator. Time is inversely related to the, or proportional to the rate with which we travel. Kind of makes sense in a way, because if the speed increases on an object, then the travel time will decrease. If the speed decreases, the travel time would increase. So this would be the inverse variation that would describe number 14. Any questions about number 14? Notice all these variations have a constant of variation. Everyone does. All right, number 16 here says the volume V of a rectangular solid, which is a box, varies jointly as the length L and the width W of the solid. Notice you don't see the word inversely anywhere in here. So all these variables, V, L, and W are going to be on the same level. Essentially, they're going to be in the numerator. So therefore, the equation that would represent this joint variation is to say V is equal to K times L times W. And this would be your result for number 16. The volume of a box varies directly as the length and the width of the box. Okay. Any questions about that one there? Number 18, the variable n is directly proportional to the square of lowercase sigma and inversely proportional to the square of E. Okay. This symbol here comes from the Greek alphabet. It is called lowercase sigma. That is its name, sigma, but it is lowercase sigma. This would be uppercase sigma from the Greek alphabet. A lot of symbols are used from the Greek alphabet in mathematics. Lowercase sigma usually represents the standard deviation of a population in statistics. Okay. Anyways, it says n varies directly as the square of lowercase sigma and inversely as the square of E. And that would be the joint variation that would relate n, sigma, and E. Any questions how we set that up there for number 18? So notice any variable or variables that appear after the word inversely always belongs in the denominator. If you don't see the word inversely, you're not going to see any variables in any appearing in any denominator. All right, and number 20, the variable D varies jointly as n and V, and inversely as the cubed root of T. So to write number 20 as a joint variation, I would say D is equal to K times U times V, and this will be sitting over the cubed root of T. And this would be the equation that we would use to describe that joint variation between D, U, V, and T. And that would be your answer. Okay. So any questions how we're writing either direct, inverse, or joint variations here? All right, now the next set of problems are going to have us go further. They're going to have us actually find the value of K, the variation constant, and to do so, of course, they're going to have to provide us with data. And then ultimately, we're going to be asked to answer questions. All right, so let's move on here. Next set of problems, 22 through 28. Now it says in this batch to find the constant of variation K. So they actually want us to, determine what K's value is. The first step is always to write the variation, and then using data, you can then find K. And then if they ask you any further question, you can use the specific variation to answer the question. So number 22 says M varies directly as X. So M is equal to K times X. All right. And it says when X is equal to 10, it implies that M takes on the value of 42. So first we're going to write the variation as an equation. M varies directly as X. So M is equal to K times X. They indicate that X is equal to 10. When X is equal to 10, M is 42. We can use this data here to determine K's value. So to do that, I'm going to replace X with 10 and replace M with 42. Hence our equation becomes 42 is equal to K times 10. And now I solve for K by dividing both sides by 10. Hence I get K is equal to 4.2. Now that we know K's value, you're welcome to write the specific variation, which would say M is equal to 4.2 times X. But all they really want us to do is just to find K. Any questions how we determine K's value there? So first write the variation as an equation, then use data to determine what K's value is. All right, let's see, what number was that? That was number 22. All right, number 24, T is inversely proportional to X. When X is 50, T is 200. Use that information to find K. So first of all, we're going to write the equation that expresses the variation in number 24. It says T is inversely proportional to X. So T is equal to K over X. And they indicate that when X is equal to 50, this implies that T is equal to 200. So here we go. K is inversely proportional to X. And when X is equal to 50, T is equal to 200. They want us to find K. To do that, we basically substitute in what we know. In for T goes 200. And in for X, we replace the number 50. Okay, so now we just have to solve this equation for K. It's that simple. So we're going to multiply both sides by 50. Got to multiply the right side of the equation by 50 also. On the left side, we're going to have 10,000, and so that's what 10,000 would be. K would be equal to is 10,000. Any questions here? How we're identifying what K would be so far? Okay. All right, that's number 24. All right. Try number 26. It says N varies jointly as T and P. When T is 2 and P is 2.5, N is 15, find K. So for number 26, N varies jointly as T and P. So N is equal to K times T times P. And when T equals 2 and P is equal to 2.5, they indicate to us that N is 15. And using this data, they want us to find K. Okay. So first I wrote the variation as a joint variation. N varies jointly as T and P. Now to find K, I replace N with 15. Replace T with 2 and replace P with 2.5. And now I'm going to have to solve for K. So 15 is equal to 2 times 2.5 is 5. divide both sides by 5, and this implies then that k is equal to 3. So that's what k would be equal to. Okay. All right, any questions how we're doing these problems here? Given some data, how we can, using a variation, find k, the variation constant. All right, so classwork number 1, today is the 2nd day of November already. I would like you to try to do a couple problems here. All right, I would like you to do problem number 27, A and B for classwork 1. So the values of y equals 4 when x equals 10, find y when x equals 5. If y varies directly as x, and b, y varies inversely as x. Okay, so here's what you're going to have to do. First, you're going to have to set up the equation that represents the variation. Then you're going to have to find k. And then once you find k, you can then answer the question that they're asking. Okay, so try number 27, A and B. Classwork number 1. All right, so 27A and B, we're having you just go a little bit further than what we've been doing. Number 27A, they say y varies directly as x, so the equation would be simply y equals kx. And they indicate that y equals 4 when x equals 10. And then they ultimately want us to find y when x equals 5. Okay. So the first thing we need to do is find k. To find k, we use this data right here. Replace y with 4, replace x with 10, and then we have to solve for k. So therefore k is going to be 4/10, which after you reduce this would be 2/5. Okay, just leave it as a fraction. Now we know that k is 2/5. Our variation becomes specifically y equal to 2/5 x. Now to find y, when x is 5, we just replace x with 5. So y is going to be 2/5 times 5, or 5/1, which means y is going to be equal to 2. And that would be your answer. So y is 2. All right. Does that make sense? Hopefully you got that there for that one. Now 27b, it says y varies inversely as x, I believe, correct? Let's see, was that what it was? Yes. Okay. So y varies inversely as x, so y is equal to k over x now. And then we have to find k. To find k, we replace x with 10 and y with 4. Solving for k by multiplying both sides of the equation by 10, we get 40. So k is equal to 40. Hence, our inverse variation specifically becomes y equal to 40 over x. And now to answer the question, what would y be when x is 5? We just replace x with 5. And we get y is equal to 8. And we're done with that problem. Any questions how we did those there for classwork number 1? All right, classwork number 1. Any questions? Okay. All right, I just want to do a couple more problems. So some of these remaining problems become a little bit more wordy. I wanted to do one like number 30, let's see, number 36 here. It says the area of a picture projected on a wall varies directly as the square of the distance from the projector to the wall. Okay, so we can draw a little picture of that here. So here's a projector, and it projects an image to the wall. And that image is going to be in the form of kind of like a square here. All right, so that's the projected image on the wall here. And this would be the distance between the projector and the wall, distance D. And the area of this projected square image would be A for area. Okay. All right, so a little picture there helps out with number 36. And let's read this again here. It says for number 36, the area of a picture projected on the wall varies directly as the square of the distance from the projector. So the area of the image projected on the wall varies directly as the square of the distance between the projector and the wall. So that's how we would write our direct variation there. And now it says if a 15-foot distance produces a 36 square foot picture. So if our distance is 15 feet, the projected area on the wall would be a 36 square foot image. And they want to, armed with that knowledge, they want us to determine the area of the picture when the projection unit is moved to a distance of 25 feet from the wall. They want us to find that area. So what do you think, Liz Ullman? I don't know if you ever experienced this or not, but the closer the projector is to the wall, is the area of this projected image going to be smaller or greater? Is it going to get smaller or greater if you move the projector closer to the wall? Anybody want to take a guess?
Smaller.
All right, it will get smaller and smaller and smaller. And the further you move this image, the projector away from the wall, the image gets larger. That's because these rays, these light rays are diverging. They're moving apart from each other. And the further you go away from the lens here, what happens is your image gets what? Larger and larger. Do you agree? So your image gets larger and larger and larger. All right. Because these rays are moving further apart from each other. So therefore, if we're going to move 25 feet, we're going to move the projector 25 feet away from the wall as opposed to 15 feet. We would suspect our final answer is going to be larger than 36 square foot for the projected image. So when we get done doing this problem, we better get something greater than 36 square feet. Otherwise, there's a mistake somewhere. Okay. All right. So how do we do this problem? First, we need experimental data to find the variation constant K. So we're going to use this data. In for A goes 36 square feet. You know, in the sciences, you actually have to take very good care of the units too. If you take a course like in chemistry or physics, the units are critical and you have to pay very close attention to them and make sure that they're coming out correctly. So I'm going to put the units in and show us how the units kind of work. The distance is going to be 25 feet, but we're going to have to square that distance. So we got 25 feet quantity squared. So solving for K, we're going to have 36 square feet is equal to 25 feet times 25 feet, I believe, is 625 square feet. That's going to be multiplied by K. Solving for K, we divide both sides by 625 square feet.
Shouldn't you be using 15 though?
What's that?
Should you be using the 15 feet though?
Yeah, why am I using 25? Yeah, you're right. No, we're not ready for 25 feet. Yeah, 15 feet is what we should be using. Thanks for that. So we got 36 square feet is equal to K times 15 feet squared. And so 36 square feet is equal to, now 15 feet times 15 feet, I believe is 225. So 225 square feet times K. Now we solve for K. And we do so by dividing both sides by 225 square feet. Now, something interesting happens on the left side. Notice these units of square feet drop out, and we're left with a dimensionless ratio here, 36 over 225. And that's what K is going to be equal to. So the units just basically drop right out of the picture here. And let's see. You know, I think this does reduce 36 over 225. I believe that 9 will divide into 225, and I subjected this number to the 9's divisibility test. 2 plus 2 is 4, plus 5 is 9. Since 9 divides into 9, 9 divides into 225, and I know it divides into 36. So we can reduce down by 9 and get this down to 4 over 25, I believe.
Yeah.
All right, so that's what K is. Now that we know what K is, we can, you know, ultimately begin to answer our question. Our question was this here: when we move the projector 25 feet away from the wall, how large is the projected area going to be? Well, our specific variation now becomes area is equal to 4 over 25 K times D squared. Now to answer this question, let's let D take on the value of 25 feet now. So we replace D with 25 feet. And that's 25 feet. That's going to have to be squared. And notice the units are going to work out just perfectly, because when you square feet, you get square feet. And those are also the appropriate units for area. So notice we've taken good care of the units, okay? And like I said, in the sciences and engineering, when you're working with computations, the units have got to work out. If the units don't work out, then that's an indication that there's a mistake somewhere. You used the wrong formula, or you put the numbers in the wrong place, okay? So anyways, we get our area is equal to, now 25 feet times 25 feet is 625 square feet. So it's going to be times 625 square feet here, and this is just over 1 here. And therefore, the projected area of the image on the wall when the projector is moved 25 feet back from the wall, notice 25 divides in itself, will divide into 625 25 times, and that'd still be square feet. And then 4 times 25 square feet is going to be 100 square feet, and that would be your answer. That would be the area of the image projected on the wall if the projector is 25 feet away from the wall. Any questions how we move through that problem there? Okay. And that makes sense that the area would be larger than what we had originally, because we moved the projector 10 feet further away from the wall. And that would indicate, just by looking at this picture here, that, yeah, I mean, that projected image is going to grow larger just by virtue of how the rays of this light diverge away from each other further you go from the lens. Okay. Make sense there, that problem? Okay. So that's a classic problem. That was number 36 in your textbook. Let's try number 40. All right, number 40 here, the resistance of a wire varies directly as the length and inversely as the square of its diameter. 50-foot wire with a 2/10 inch diameter has a resistance of 125 10,000ths. This symbol, which is called uppercase omega, comes from the Greek alphabet. It's used in electrical circles to represent ohms. Ohms is a unit of resistance in electronics, okay? Ohms is a measure of how a wire resists the flow of current through it, all right? Some wires have a very large resistance, like the wires in your toaster. And because of that, when you fire it up, the wire starts to glow because there's a tremendous amount of resistance through the wire. And that resistance in that case is good because it delivers heat, which cooks our bread and forms our toast. You also have wires in your hair dryer or hair blower in your bathroom. When you click that on, the wires have a very high resistance, and the current still wants to try to get through the wires, but to do so, it has to meet with that tremendous resistance, creating a lot of heat. And that heat is good because it dries your hair. So in some cases, resistance is good, but in other cases, it can be very bad. It can actually cause fires too, if there's too much resistance on a wire that's not able to handle the load, okay? Then you can have a fire breakout, so that can be a bad thing. So resistance is good and bad. So how did I get on this question here? All right, well, it says the resistance of a wire we'll call R varies directly as the length of the wire we'll call L, and inversely as the square of the diameter, which we'll call D. First of all, ladies and gentlemen, you have to write the equation that represents the variation. I mean, there's no way you're going to answer any of this question or any question until you first write the equation or the variation. So how would I write this as an equation? Well, the resistance R varies directly as the length and inversely as the diameter of the wire, inversely as the square of the diameter of the wire. So therefore, this would be the equation that is in order for this problem here, where R represents the resistance of a particular metal or wire. And the units are going to be in ohms, and they use this symbol to represent ohms, okay? So L represents the length of the wire, Did they indicate the units of the length? Was it feet, meters? Feet. Okay. So length is in feet, and D represents the diameter of the wire. Okay. So since we're talking about a diameter, the cross-sectional view of the wire would be a circle. So we have a conductor in the form of a wire, some sort of a metal in the form of a cylinder here, and we're going to try to pass a current through the wire. Normally they use I to represent current and electricity. Okay. And the opposition that these electrons meet up with is called the resistance. All right. So, ladies and gentlemen, there's our equation that models the resistance of this wire versus its length. And its length would be this dimension here. And the diameter is going to be this dimension here, cross-sectional diameter. Okay. All right, let's go back and read this problem again. It says a 50-foot wire. So therefore, if the length is 50 feet and it has a diameter of 0.2 inches, has a resistance of 125/10,000 ohms. So 0.0125 ohms. Then they want us to find the resistance of a 40-foot wire with a diameter of 1/10 of an inch. Okay. Well, before we can do that, we got to find K. So to find K, we're going to use all this data here. We're going to substitute the values into our equation that we wrote. So in for resistance goes 0.0125. I'll leave the units as part of our computation so you can see how the units play out. That's going to be equal to K times the length being 50 feet, over the diameter, which is 0.2 inches, and we have to square that. And now we got to solve for K. All right, 0.2, 2/10 times 2/10 is 400ths, which is going to be 0.04. So this is going to be 0.0125 ohms is equal to K times 50 feet over 0.04 square inches. To solve for K, I'm going to multiply both sides by 0.04 square inches and then divide by 50 feet. So therefore, this implies that K is going to be 0.0125 ohms times 0.04 square inches divided by 50 feet. So let's get on our calculator and dial this up. See what we get. Anybody got a calculator handy? Multiply this by this and divide by 50 and tell me what that number should be.
0.04,
0.04.
I believe. Oh, sorry. 1 second. Sorry, I put in the wrong thing.
Okay. All right, I worked this out. Anybody getting this? Is a small number. I'm getting like 0.00001. Can anybody confirm that?
Yes, that's also what I got.
And the units will be ohms, square inches divided by feet per feet. Okay, those would be the units. Okay. Now, units do clutter up our computation. There's no doubt about that. But like I said, you get into the sciences or engineering, ladies and gentlemen, you have to make sure your units work out perfectly fine. And for that reason, it's nice to start to get in the habit of working with your units. So this would be K. Therefore, our specific joint variation now says the resistance of this wire is going to be equal to K, but K is 0.00001. And this is going to be ohms times square inches per feet And this is going to be times L, the length of the wire, divided by the diameter, the square of the diameter of the wire. Okay. All right, now we can answer the question. The question now is that we accomplished all of that. They're going to ask us, okay, what would be the resistance in a wire that is 40 feet long? So if we have a wire that measures 40 feet of length, and the cross-sectional diameter is 0.1 inches, what would be the resistance of this new wire here now? Okay. Well, we can see here, ladies and gentlemen, with this relationship that if you increase the length of a wire, the resistance of the wire is going to increase. You increase the cross-sectional diameter of the wire, the resistance decreases big time. And that's why like 12 gauge wire has a larger cross-sectional diameter as opposed to like 8 gauge wire, which is a very small cross-sectional diameter, right? But to carry large loads of current and voltage, you need a large diameter wire, all right? And most housing construction requires 12 gauge or at least 14 gauge wire. So you can see that if you're going to push more current, more power through this wire, you better have a larger cross-sectional diameter, okay? If you try to push a large current through a wire with a small cross-sectional area, what's going to happen is the wire will overheat. Too much resistance, it'll overheat, and it will literally melt right in two. You'll have an open or a short then. Now, you'll not have a short, you're going to have an open, okay? And your circuit will die. And you could also meet with a fire hazard too. So, all right. So let's find out what our resistance is going to be for this new wire. Let's put 40 feet in for L and put 0.1 inches in for the cross-sectional diameter. And let's compute the resistance. And I'm going to show you how the units work out perfectly, okay? So we got 0.00001 ohms square inches per feet. And that's going to be multiplied by the length of the wire, which is 40 feet. And then this is going to be divided by the diameter, which is 0.1 inches squared. All right, get on your calculator and see if you can bring this up. 0.0001 times 40 divided by 0.1 squared. You tell me what you get, and I'll show you how all these units work out too. So, all right, so 1, 2, 3, 4 ohms inches squared per feet times 40 feet. And this is 1/10 times 1/10, which would be 1/100th. So this is going to be 0.01 1/100th square inches here. All right, let me know if anybody dials this up correctly, multiplying this by this and dividing by this. So what do we get for the resistance in this wire here?
I got 0.004.
All right. All right, let's double check that. 0.00001 times 40 divided by 0.01. I'm getting like 0.04. Do you have too many zeros in there or something? 0.04. I'm getting like 400s.
Oh, I did it by 0.1.
Okay. 0.04. Can anybody else confirm this? Did I do that right or not? Maybe I'm wrong. Okay. Now look at it, ladies and gentlemen. Check these units, how they work out. Look at the square inches.
Isn't it supposed to be all of that's divided by 0.1?
No, this is 0.1
Squared.
squared.
Yep, I see it. All right, thank you.
Which is 1/10 times 1/10 is 1/100th, so 0.01. All right. Now check out the units here. Check this out. Square inches drops out with square inches. Feet cross cancels out with feet. And we're left with what units? Ohms, the proper units for resistance. So we've taken good care of our units. See how the units have to work out just as well as the number? It's very important when you do scientific calculations that your units come out correct, okay? Otherwise, there was a mistake made. So you always want to check your units, do a little unit analysis, and make sure units are coming out correctly. So that'd be the resistance of this 40-foot long wire. It would be 4/100ths of an ohm. And I have a question for you. Is 4/100ths of an ohm larger or smaller than 125 10,000ths of an ohm? What is it? Smaller or larger? You think that's smaller or larger?
Larger.
Yeah, in fact, it's about 3.2 times larger. All right, 3.2 times larger. Does anybody want to indicate to me why the resistance of this wire has increased compared to this wire here? Why is this resistance larger? Anybody want to just argue that? What's happened here? We've gone with a length of 50 feet. We reduced our length by 10 feet. Do you agree? The resistance should drop down. But what happened to cross-sectional diameter, though? We decreased the cross-sectional diameter. In fact, we have the cross-sectional diameter. We went to a smaller diameter wire. And you can see, ladies and gentlemen, that the major player here is not really the length, it's the what? It's the cross-sectional diameter. Do you agree? That really, in a large part, determines the resistance of a wire there. Okay. Yeah, so you go to a smaller cross-sectional diameter wire, your resistance is going to increase significantly. All right. Okay, that was one like number 36 there. Any questions about that one there? All right. Now I want you guys to do number 44 here for classwork number 2. It says the strength of a wooden beam varies jointly as the width of the beam, W, and the square of the thickness of the beam, thickness being T, and inversely as the length of the beam, L. A beam that is 48 inches long, 6 inches wide, 2 inches thick, can support a load of 417 pounds. Find the maximum load that can be safely supported by the board that is 12 inches wide, 72 inches long, and 4 inches thick. You guys go ahead and do that problem. That's classwork number 2, number 44 on page 390 in your textbook. First, you have to set up the equation that represents the variation, and then you go from there. Okay, so see if you guys can get that done. All right, I used S for strength of the board. You may have used some other variable. It doesn't really matter what you call it. But anyways, they give us some data here with which to find the variation constant. This would be the joint variation equation that's necessary. And now to solve for K, I just substitute in the values where they belong. And I did simplify this down. 2 inches squared is going to be 4 square inches times 6 inches is going to be 24 cubic inches divided by 48 inches. Is going to be 1/2 square inches, because cubic inches divided by inches reduces down to square inches. Now to solve for K, I'm going to multiply both sides. Actually, I'm going to divide both sides by 1/2 square inches. And so K is actually going to have, when I multiply, I would actually, by dividing by 1/2, it's like multiplying by 2. So 2 times 417 is going to be 834. And the units are going to be pounds over pounds per square inch. That's what K's units are going to be here. Okay. All right, so therefore the strength of my board is now going to be equal to 834. I'm going to have pounds per square inch. Pounds per square inch are actually units of pressure. I don't know if you're aware of that. Times W times T squared over L. Now we can answer the question. And the question was, find the maximum load that a board can safely support if it is 12 inches wide. So if the width is 12 inches and the length is 72 inches and the thickness is 4 inches. Okay. So now to answer this question here, we just have substitute the values into our joint variation. So we got 834 pounds per square inch. I'm leaving the units in because I want to show you how the units work out. Times W, which is 12 inches, times T squared, which is the thickness squared, 4 inches squared. And this is divided by the length, which is 72 inches. All right, so when we get, dial this up on our calculator here, we got 834 times 12 times, this is going to be 16 divided by 72. And the units that are going to work out here is we're going to have pounds per square inch times, this is going to be square inches times inches is cubic inches. And this is all divided by inches down here. So what happens to these units here? Well, square inches cross cancels out with 2 of these inch units, leaving behind inches. And inches divided by inches, the inches drop out, leaving you with pounds, the correct units for strength. So the units work out perfectly correct. All right, anyways, get on our calculator and dial us up and see what we got here. So it's 834 times 12 times 16. And then we're going to divide that by 72.
2,224.
Exactly. And the units would be what? The units that survive are pounds, because everything else cancels here. And those are the correct units for strength. By the way, a ton is 2,000 pounds. So this is just a little bit more than a ton that this board can support. Okay. That's quite a large amount of weight that this board can support here. Any questions about this? 2,224 pounds is what this board can support if it has these dimensions here. Okay. All right. All right. I want to show you something interesting, ladies and gentlemen. I'm going to use this equation we developed, this joint variation equation. What if we double the length? What if we keep the width and the thickness the same of a board, but we double its length? How would that change the strength of the board? We're going to argue that mathematically now. So therefore, suppose that I have a new length, which is going to be twice the old length, or twice the original length. I'm going to double the length. How will the strength of this board change? Well, the new strength is going to be equal to K times the width times the thickness squared divided by the new length. Which means the new strength is going to be K times the width times the square of the thickness divided by, but the new length is twice the old length. But watch this, I can bring this 1/2 out front here and multiply it by this whole quantity, which is to say K times W times T squared over the length. But ladies and gentlemen, what is this? Wasn't this our original strength, S? So therefore, the new strength, if we double the length of this board, the new strength is only going to be 1/2 of the what? The original strength. Everybody see that there? So when you double the length of the board, the strength is reduced or cut in half. Does that make sense? Why that would be the case? The longer you make a board, ladies and gentlemen, and you put a heavy load on it at the end, what's going to happen is this board might start to what? Bend. Do you agree? If you put a heavy load on the end. So the longer your board is, it can support less weight. Shorter the board is, it can support a heck of a lot more weight. Okay? Okay? You see that there? And you do this type of reasoning in physics quite a bit here, working with formulas. All righty. All right. So that was an interesting section. Well, I'll tell you what, maybe we could do one more here. Suppose that I now, instead of doubling the length, suppose I hold the width and the length constant and I double the thickness. How will the strength of the new board change if I double the thickness, keeping the width and the length the same? Let's look at one more. Suppose now my new thickness is going to be the doubling of the original thickness. Let's now argue how the new strength is going to look compared to the original strength. Well, the new strength is going to be K times the width times the thickness, the new thickness squared divided by the length. But what's the new thickness? The new thickness is twice my original thickness or old thickness. So therefore, this is going to be K times the width times 2 times the thickness squared all over the length. But this is really going to be K times the width times 4 times the original thickness squared over the length. Which lays on, I can bring the 4 out front here and I can say it's 4 times K times the width times the original thickness squared divided by the length. But another name for this is the original strength, the old strength. So therefore, the new strength of this board is going to be 4 times the old strength. So when you double the thickness, you quadruple the strength of the board. Everybody see that there? When you double the thickness, you quadruple the strength. Pretty interesting, huh? All right. Interesting. Okay. All right. Any lingering questions on a section 3.7? As this will close down this chapter now. So chapter 3 is in the archives. Oh, I want to set the record straight, ladies and gentlemen. What I said earlier was an error. The larger the gauge number, the smaller diameter, cross-sectional diameter of the wire is. So 22 gauge wire is small in diameter compared to 12 gauge. So if you want to run an air conditioner or like a electric range that pulls a lot of wattage, you'd have to go to a very low gauge wire, maybe even a 10 gauge wire that affords you a very large cross-sectional diameter so that it minimizes the resistance and heat buildup in the wire when you try to push all that power through the wire. Okay. So I do apologize. The higher the gauge number, the smaller diameter of the wire, the smaller the gauge number, the larger the diameter of the wire. That's the way it works in electrical circles. All right, let's close that section out. Ladies and gentlemen, one last section here this afternoon is 4.1 as we now embark on what are called inverses of functions, okay? What's the inverse of addition?
Subtraction.
Yep, and the inverse of multiplication is division. Well, just like our operators have inverses, functions have inverses. Well, not all functions have inverses. We'll discover which ones, okay? In fact, ladies and gentlemen, let's just open up the section by laying out a very important fact in mathematics. Only one-to-one functions have inverses. Only one-to-one functions have inverses. So to have an inverse, a function must be one-to-one. What is one-to-one? What's the definition of a function to be one-to-one? A one-to-one function does not have any repeated y-coordinates for any two different ordered pairs. The graphs of one-to-one functions must pass a test. And that test has a name. It's called the horizontal line test. Didn't we have a test before called the vertical line test? Does anybody remember what the vertical line test was used for? A vertical line test.
It was testing to see if something was a function.
Yeah, it was used to test to see whether or not a relation qualified as being a function. But I'm telling you, these are functions. Okay, they're already functions. Their graphs already passed the vertical line test. Now the graph has to pass what's called the horizontal line test in order to qualify as being a one-to-one function. So let's look at an example of a graph of a function here. All right, this is definitely the graph of a function, our basic parabolic graph, whose parent function is f of x equals x squared. Is this function one-to-one? It's a function. This relation is a function, but is it a one-to-one function? The answer is no, because you can place a horizontal line somewhere in the x and y plane, and that horizontal line can touch the graph in more than one point. This is not a one-to-one function. And therefore, like I'm not being a one-to-one function, there would be no inverse for this function. No inverse. No inverse for that function there. Let's take a look at this one here. Would this function be one-to-one? Yes, this is a one-to-one function because no matter where you put a horizontal line, it only touches the graph and at most one point anywhere. So this is an example of a one-to-one function. And therefore, this function would have an inverse. So this function would have an inverse, okay? You see, this is not a one-to-one function because you have two different points on your graph that share the same y-coordinates. Y-coordinates are the same with these points, and that's why this is not a function. Nowhere on the graph of this function here do you have any two different ordered pairs with the same y-coordinates. All the y-coordinates are unique or different. That's why this is a one-to-one function. All right. Would this function here be one-to-one? This is definitely a function, but is it one-to-one? The answer is no. You could place a horizontal line somewhere and have that horizontal line touch the graph in more than one point. So this is definitely not a function, a one-to-one function. It's a function, but not one-to-one. Because in this case, if I put my horizontal line here, I could discover that there's four different ordered pairs with the same y coordinates. So it's not one-to-one. There would be no inverse for this function. Okay. Horizontal line test. All right, suppose I have a function f defined to be this finite set of ordered pairs here. Is this a one-to-one function? Well, I can't even call this a function. Why not?
2 repeats.
These are repeated x coordinates. This is just a relation. It's not even a function. Okay. So we shouldn't even consider something like that. All right, let's try this one here. Is this a one-to-one function or not? Is it a one-to-one function? Why is this function not one-to-one?
4 shows up twice as a y coordinate.
Exactly. We have the same y coordinate appearing in two different ordered pairs. So this is not one-to-one. You know, instead of saying 1-2-1, sometimes textbooks just shorten it up to say 1-1. It's not a one-to-one function. This means the same thing as one-to-one. There would be no inverse for this function here. All right, there is a theorem. Ladies and gentlemen. And this theorem says this. Suppose we have a one-to-one function f. Then we say that g is an inverse function of f. In other words, g is equal to f inverse. You see this notation here? You do not read this notation as f to the -1 power. Inappropriate. You read this notation as f inverse. We say that this function g is the inverse of function f, denoted as f inverse, if two things are true. If f composed with g of x gives you x, and g composed with f of x also gives you x. If both these conditions are true, then that's enough to say that function g and f are inverses of one another. They're inverses. In other words, this theorem is saying that it's always true that a function composed with its inverse will always give you x, regardless of the order of composition. Everybody see that there? So this is a test to determine if two functions qualify as being inverses, is just to subject them to the composition operator we looked at when we were discussing the algebra of functions in the past. All right. So very important theorem here. We understand that there? All right. Well, let's have a little bit of fun. It says, given, suppose f of x is this linear function here. And it's not really written in strict slope-intercept form, but it's pretty darn close. G of x is this function here. By the way, this is also a linear function, because you could write this in slope-intercept form too, just by splitting this up, putting x over 12 minus 100 over 12. Question is this: are these inverses? Are these functions inverses of each other? F of x and g of x? Well, we can use the theorem we just looked at. Let's look at f composed with g of x. F composed with g of x is going to be f of g of x. Put x in the function g and out comes this expression. This expression now will become the input in the function f. So in the function f, we put x minus 100 over 12. So this x minus 100 over 12 becomes the input in the function f, which means this expression drops in for x in the definition of function f. So function f evaluated at this expression is going to be equal to 100 plus 12 times x minus 100 divided by 12. Now what happens to these 12s here? They drop out and we're left with 100 plus x minus 100. Now notice the hundreds drop out here, and heck, we're left with x. Everybody see that there? So f composed of g of x does simplify down to x. That's still not enough to say that f and g are inverses. We now need to look at the composition g composed with f of x, which by definition is going to be g of f of x. Which when you put x in the function f, out comes 100 plus 12x. Well, 100 plus 12x now is going to become the input in the function g. So this 100 plus 12x now is going to come up here and drop in where you see x in the definition of function g. in for this x here is going to go 100 plus 12x right in here. And then we simplify. Well, the hundreds drop, and we're left with 12x over 12, which reduces down to, well, I'll be darned, reduces down to x. And so therefore, ladies and gentlemen, since f composed with g of x is x and g composed with f of x is x, we say that g and f are what? They're inverses. So that's to say that g is really equal to f inverse, or that's to say that f is really equal to g inverse, however you want to coin it. The bottom line is they are inverse functions of each other, okay? So these are inverses of each other. Does that make sense, sir? How we verified that those functions are inverses of one another using the composition operator. And that theorem we see there. All righty. That makes sense? Any questions about this here? Well, the next logical question is this. Yeah, we just got done showing whether functions are inverses of each other. The next logical question is, given a function, how would we, given a one-to-one function, how, ladies and gentlemen, would we find the inverse of such a function? How would we do it? Well, suppose, first of all, our function, our one-to-one function, is depicted as a finite set of ordered pairs. Now, here's a relation that is a function. And is this a one-to-one function? If you were to plot these points in the xy plane, would a horizontal line placed anywhere cross through any of these? Would a horizontal line placed anywhere cross through more than one of these points? In other words, are there any duplicate y coordinates for any two different ordered pairs here?
No.
No, all the y coordinates are unique. So this is definitely a one-to-one function. So it must have an inverse. It's a one-to-one function. Well, how do we find the inverse? Well, it's pretty simple. The inverse function, denoted as f inverse, is basically going to be a set of ordered pairs where the x and y coordinates become interchanged. So the 0.13 found in function f is going to be the 0.31 found in the inverse of function f. 2,5 becomes the 0.52 in the inverse. 310 becomes 10.3. 420 becomes the 0.24 in the inverse. And you are looking at your inverse function there, which also is one-to-one. Notice the inverse function is one-to-one. Okay. Something interesting occurs here based on what we just observed. What is the domain of function f? The domain, again, consisting of all the x coordinates of all points that define the function. So the domain would be the set consisting of 1, 2, 3, and 4. That's the domain of function f. What is the range of function f? The range being the set of all y coordinates of the point for function f. That would be the set consisting of 3, 5, 10, 20. But I have a question for you, ladies and gentlemen. What is the range of the inverse function? What's the range of the inverse function? The range of the inverse function is a set of y coordinates of the inverse function. 1, 2, 3, 4. So the domain of the original function f is really the range of the inverse function. Interesting. And the range of the original function happens to be equal to the domain of the inverse function. The domain of the inverse function being a set consisting of 3, 5, 10, and 20. So this is something very important to understand, is that when we're talking about a function and its inverse, the roles of the domain and range become interchanged. Okay. To represent this function using this like set picture here. This would be function f here, the domain of which consists of 1, 2, 3, and 4, the range of which consists of 3, 5, 10, and 20. Function f, we say, maps 1 to 3, 2 to 5, 3 to 10, 4 to 20. The inverse function, ladies and gentlemen, turns around and reverses the roles here. It takes 3 and maps it back from whence it came back to 1. 5 gets mapped back to 2. 10 gets mapped back to 3, and 20 goes back to 4 by the inverse function. So the domain of the original function is really equal to the range of the inverse function. And the range of the original function is really the domain of the inverse function. Interesting to note the relationship between the domain and range of a function and its inverse. Okay. Any questions about that there? So it's pretty easy to determine the inverse of a one-to-one function if it is portrayed as a set of ordered pairs. All you do is interchange the x and y coordinates, and boom, you got your inverse function. But unfortunately, oftentimes our function is not represented by a finite set of ordered pairs. Oftentimes it's represented by an equation. And so, ladies and gentlemen, how would we find the inverse of a function if it's given to us in equation form? Well, in order to do this, we follow these steps here. Step number 1 is, first of all, we replace functional notation. We replace the functional notation with y, because y just looks simpler and nicer to work with. Number 2, the second step, we interchange x and y. Y is replaced with x is replaced with y. Step 3 is then we solve for y. Step 4, we then wrap up the problem by replacing y with inverse notation. And that's it. That's how, in general, you find the inverse of a function if it's given to you in equation form. Now, it has to be a one-to-one function. That's the requirement. Otherwise, you can't even do this. All right. So it has to be one-to-one. So let's see if we can put this into practice here. Let's try to find the inverse. Let's say f of x equal to like 3x minus 1. Let's find the inverse of this simple linear function here. First of all, do you think this is a one-to-one function? Well, if you were to take the time and graph this linear function, notice we're lucky here. The graph, or excuse me, the function is in slope-intercept form. So the y-intercept is -1 down here, and the slope is positive 3 over 1. So 1, 2, 3, up 3 over 1, correct? And we would have the graph of this linear function, and this would be its graph here. You can see that this function is one-to-one because it does pass the horizontal line test. No matter where you place a horizontal line in the xy plane, a horizontal line would touch the graph and at most one point. This is a one-to-one function. So it is one-to-one. Therefore, it must possess an inverse. How to find it? Well, we use our steps here. Step number 1. I replace functional notation with y. So I'm going to replace f of x with y. That's simple. Step number 2 is I interchange x and y. So y becomes x becomes y. Step number 3, I'm going to solve this equation for y. How to do that? We add 1 to both sides. Then I divide both sides by 3. Hence, I have y is equal to x plus 1 over 3, in which case I can split this up. I can say this is really 1/3 x plus 1/3. Everybody see that there? So what did I do again? I replaced f of x with y. I interchanged x and y. Then I solve for y. And I get this function here. Last step now is to replace y with appropriate inverse functional notation. And since our function was f of x, we will denote this as being f inverse of x. And ladies and gentlemen, we have our inverse function. These are inverses of each other. Now, if you were to take the time to graph this, you would see that it's a linear function with a y-intercept of 1/3 and a slope of 1/3. So the y-intercept would be positive 1/3, and the slope is positive 1/3, which means for every 1 unit we go up, we go over 3 units. So we'd be like way over here. So basically put, the graph of our inverse function is going to look like this here. So this is the graph of f of x. This will be the graph of the inverse function, f inverse of x. Does it seem like this is the inverse of the original function? Well, when I wrote it this way, when I solved for y, which is x plus 1/3, you can really see it here. Not so much when I split it up like this, but you can really see it here. Because what's the inverse of subtracting 1? The inverse of subtracting 1 is what? Adding 1, correct? What's the inverse of multiplying by 3? Dividing by 3. And we're dividing by 3. Kind of makes sense that this is the inverse of this. You can kind of see it. There's a very important fact, ladies and gentlemen, as far as the graphs of a function and its inverse are concerned. It's always true that the graph of a function f and its inverse, f inverse, are always symmetric. They're always going to be symmetric with the line y equals x. So when you graph a function and its inverse in the xy plane, the graphs are always going to be symmetric with this line y equals x. And this would be the line y equals x, that dashed line. So the graph of a function and its inverse are always symmetric with respect to this line y equals x. That's to say that you choose this point on the graph, the perpendicular distance it is away from this line of symmetry is the same distance as this point is here. Now, it doesn't look like it because I should have used graphing paper, but basically put, later on, we get perfect symmetry here, okay? Perfect symmetry. That's always true. So when you graph a function and its inverse, it better always be symmetric with respect to y equals x. That's another way to determine visually if functions qualify as being inverses, is by looking at their graphs and seeing if they are indeed symmetric with respect to y equals x there. Okay, so let's all right, did that problem make any sense there? All right, let's see about this function here. F of x equals x squared. Now, the basic parent function is going to be x squared. What happens to the graph of the basic parent function when I add 4 to the function? What happens to the graph?
Goes up by 4.
All right, so the basic parent function, quadratic function, f of x equals x squared, which is going to be the basic parabola opening upwards with vertex at the origin, is going to be now a parabola opening upwards with the vertex at 0, 4. Do you agree? So using our transformation knowledges of functions expedites our ability just to sketch this graph here. All right, but I have a question for you. Is this function 1-to-1? This is not a 1-to-1 function because the graph fails the horizontal line test. You could put a horizontal line maybe right here and it would cross the graph at more than 1 point. It's not 1-to-1. This is a big problem because as it is, ladies and gentlemen, this has what? No inverse. No inverse because it's not 1-to-1. And yet I want to try to find the inverse. So what's going on here? Well, here's what's going on. With this situation here, we're going to have to force this function to be 1-to-1 before we can actually find its inverse. To do that, we're going to have to force it to become a 1-to-1 function. And the way to do that is to basically just restrict the domain of this function. In particular, what I'm going to do is I'm going to restrict the domain of this function to only consist of only non-negative real numbers. So from 0 to infinity is going to be the domain. Now, if I restrict the domain of this function to become this, that means we're going to lose the left branch of this graph. We will not see the left branch. So we must erase it. So the left branch is gone. Now, is this a 1-to-1 function? Now it's 1-to-1. Do you agree? Because we restricted its domain. Now we can find the inverse of this 1-to-1 function. And furthermore, we know that the domain of this function here, ladies and gentlemen, will be equal to the range of the inverse function. We know that the range of this function, this function here, and the range would be from 4 to infinity, is the domain of our inverse function. Everybody see that there? Okay. Now, how do we find the inverse? We use our little recipe, our 4-step recipe. First, I replace f of x with y. Step number 2 is I interchange x and y. Step number 3 is I solve for y. I have to solve for y now. To do that, I subtract 4 from both sides. Therefore, I'll have y squared is equal to x minus 4. Now, to solve for y, we have to get rid of the square. We do that by taking the square root of both sides. Now, I have a question for you, ladies and gentlemen. Normally, we take the plus or minus square root of the right side, as we were taught in the past. But look at the range of my inverse, the range of my inverse function must consist of only what? Non-negative real numbers, because it must be equal to the domain of my original function up here. Isn't that true? So if the range of my inverse function is to consist of non-negative real numbers, would I have a negative sign in front of this square root or only a positive sign? What do you think? What sign has to disappear here if the range of my inverse is to be this?
You can only have positive.
That's right. We got to get rid of the negative sign, because the range of our inverse function can only, output a positive value, a non-negative value. So away goes the negative sign here. Very important. All right, the negative sign's got to go. Therefore, we have y is equal to the positive square root of x minus 4. Now all we do is replace y with the appropriate inverse functional notation. And since our function had f of x for its notation, the inverse notation for the inverse would be f inverse of x. And that's equal to the square root of x minus 4. You are looking at the inverse. Therefore, these are inverse functions of one another. And furthermore, the domain of this inverse function is going to be equal to the range of the original function, which is to say 4 to infinity. And that kind of makes sense, because remember, underneath the square root, we can only have non-negative real numbers. So that means this x minus 4 would have to be set greater than or equal to 0, which means when you solve for x, x would have to be greater than or equal to 4. That makes sense, ladies and gentlemen, that the domain of my inverse must be this. Isn't that true? Isn't this saying greater than or equal to 4? Kind of makes sense here. And therefore, the range of my inverse function, which is the domain of the original function, must consist of only real numbers between 0 to infinity. Now, if I was to graph this inverse function, how would the graph look? Do we remember the graph of the basic square root function, which is the square root of x? Do you remember how that looked in general? That was just like this. Do you agree? So, ladies and gentlemen, how does this function's graph compare to the parent function's graph? notice that g of x is really this function evaluated at x minus 4. So what happens when we put x minus 4 in for the argument? What does that cause the graph to do? Get shifted up, down, right, or left? What do you think? X minus 4.
When right 4.
It'll go to the right 4 units. So this graph is going to go to the right 4 units. And it's going to be over here. So our inverse function, the graph's going to look like this. Let's come up here and graph it up here. So the graph of our inverse function is going to look like this. Ladies and gentlemen, so therefore this is the graph of f of x. This is the graph of the inverse function. Does it appear that these two graphs are symmetric with respect to the line y equals x? Does it appear to be the case? And it is the case, because we stated earlier with a well-known fact that the graph of a function and its inverse is always symmetric with respect to this line y equals x. Sometimes we call this the 45-degree line because it makes a 45-degree angle with the positive x-axis. So sometimes we call y equals x a 45-degree line. Okay, does that make sense there? How we found the inverse of this function by restricting its domain to force it to be a one-to-one function. And then we're able to find the inverse. All righty. Okay. Almost done. I have to show you one more, ladies and gentlemen. Well, at least to finding the inverse. Find the inverse of f of x equal to x plus 1 over x plus 2. Now, if you were to graph this rational function, you would see that it is a one-to-one function. Well, let's see. Is it one-to-one? Vertical asymptote would be that x equals -2, and the horizontal asymptote would be y equals 1, correct? Is this a one-to-one function? Well, surefire way of finding out is by graphing it quickly. So let's see if we can do that. Son of a gun. So let's see, x plus 1 divided by x plus 2. Yes, ladies and gentlemen, it is a one-to-one function, okay? It is one-to-one. So trust you me when I say that. If you were to take the time and graph this or sketch the graph, vertical asymptote is at -2. Horizontal asymptote is at y equal to 1. And if you were to graph that function, you would see that the graph would be I believe the graph goes like this here, and then it goes like this here. So you can see that it is a one-to-one function. All right. How do you find the inverse? First, we let f of x be y. Then we have to interchange x and y. Now we got to solve for y. To solve for y, I'm going to have to multiply both sides of this equation by y plus 2 to get rid of this fraction here. So we multiply the left by y plus 2. And if I was to multiply the right side by y plus 2, the y plus 2's would cancel. And we're left with this. I want to solve for y. So I'm going to have to distribute the x in here. So we got xy plus 2x is equal to y plus 1. Now I'm going to get y on one side of my equation. So I'm going to drag the xy over to the right by subtracting it from both sides. And I'm going to drag the 1 over to the left by subtracting it from both sides. When I do all this, I'll have 2x minus 1 is equal to y minus xy. To solve for y, we have no choice, but we're going to have to factor y out of both these terms here. So y is factored out, leaving behind 1 minus x. And now finally, to solve for y, we divide both sides by 1 minus x. And ladies and gentlemen, I have y. So therefore, now we go to inverse notation. So f inverse of x is going to be equal to 2x minus 1 over 1 minus x. This is the inverse function of this function. These are inverses of one another. Inverses. Everybody see that there? Inverses. All right. And this is being recorded, so you'll be able to look this over in greater detail later on there. All right. Now, I'll tell you what I'm going to do here quickly. I'm going to go to Desmos here. And I am going to try to graph these functions real quickly for us to see the symmetry. So first I'm going to graph x plus 1, the original function, x plus 1 divided by x plus 2. And then I'm going to graph the inverse. And this is the inverse, which I'll call g equal to 2x minus 1 divided by 1 minus x. And then, ladies and gentlemen, I'm going to graph one more function, call it h, which is equal to x. I have a question for you. Does it appear that the graph of the original function in red is symmetric with respect to its inverse, which is in blue? Do those graphs look symmetric with respect to the green line y equals x? Do we have symmetry? We have perfect symmetry. Do you agree? Perfect symmetry. Isn't that awesome? All right, there's just one more problem I want to show you really quickly. And you don't have to write this down. It'll be on the recording here. Suppose that we have the graph of some function f of x as being up here. This is the graph of f. Suppose I want to graph the inverse function. Well, it's pretty easy to do that. I mean, all we got to do is take these points here, which are part of function f, and just reverse the x and y coordinates and then plot the new points, and we'll have the graph of the inverse. It's really quite simple. So the point -4, -2 becomes the point -2, -4. The point -3, 2 becomes the point 2, -3. The point 0,4 becomes the point 4,0, and you have the graph of your inverse. And notice the graphs are symmetric again with respect to that line y equals x. All right, that's going to do it. I'm all out of time, so I'm going to have to let you guys go. Tell you what, I will open up the chapter 3 and 4 quiz on Alex for you. And I will also post a preview of the chapter 3 and 4 exam, which I will release on Monday. I will also show you the solutions to that preview. Please try to work through it over the weekend and prepare yourself for the exam, and bring any questions that you may have to Monday's session. I'll be happy to answer any questions that you do have. All right, if there are no other questions or concerns or comments, you have a great day, and hopefully I'll see you next week. Enjoy your weekend, and don't forget to turn your clocks back. I think we go back to standard time this weekend, I believe. Well, I think we do. All right, so take care, ladies and gentlemen. I'll see you next week.